Okay, hi everyone. It is my pleasure to introduce our invited speaker, Xiao Liang, who is an assistant professor at the Chinese University of Hong Kong. Xiao has been doing a lot of amazing work at the intersection of MPC and quantum. And today he will be giving an, I'm sure, very interesting talk on the quantum impossibility of MPC. Yeah, Xiao, please take it away.
Thanks, Lisa, for the introduction, and also thank Sophia and Peter for inviting me, and thank all of you for being here. So yeah, I'm here to bring some quantum air into this classical room. Believe it or not, like quantum is coming. I know that people in this room may hold different opinion, but you know, it's always good to get prepared first. Like, there is a reality, possible reality in the future that quantum computer will become reality. So yeah, probably we should prepare for that. And in terms of quantum, it's actually a good thing for most of the, we'll say, ordinary people or normal people. Because if you have this quantum device, you can use it to achieve many fascinating things, like for quantum algorithm design, machine learning, and programming languages. However, for cryptographers, like we think in a very conservative way. To us, the quantum computer first means quantum adversaries. So thus, the main focus of this talk will be the interaction between quantum computing and MPC. First of all, probably the first question you want to ask is, okay, what change does quantum computing cause to MPC? Even if you don't work on this area, probably you've already heard a lot of exciting progress recently in this interdisciplinary area. There are a lot of things going on, but to be honest, everything actually boils down to a single source of change, which is the quantum no-cloning theorem. Let's just quickly recap this theorem. This is an information theoretic theorem saying that you cannot make two copies of a given quantum state. Note that there is a issue of quantifier. I'm not saying that it's hard to clone any quantum state. I'm asking for a universal quantum algorithm so that it works for any given quantum circuit. This is impossible. For sure, if you have a fixed quantum state and for example, you can write down the classical expression of this fixed quantum state, or you occupy a device that can generate this specific quantum state again and again. Of course, you can clone this state. But that's not the meaning of no cloning here. No cloning here really asks for a universal quantum algorithm that clones for any given input. That's impossible. So actually, this impossibility is not a big issue for many primitives. For example, one function or CPA public encryption. For this simple primitives, probably you can simply replace the underlying assumption from DDH to something like quantum resistant. For example, LW is one of the candidates. But I do want to mention that there are some exceptions. For example, in this random oracle-ish constructions or tools, such as pseudo-random function or Fiat-Shamir transform, for these tools, like it has some relation with random oracle model in a certain sense. For these things, like you really need to think how to do the quantum proof or how to define quantum access to the random oracle. So they represent a type of exception. But that's not the main focus of today. Today this is the workshop for quantum. This is workshop for MPC. So the thing really I want to talk about today is the problem caused by non-cloning theorem to zero knowledge and MPC. What's special about them? They are interactive protocols and they are simulation-based. They need simulation-based security, and that's like could be very problematic. Why? To see the issue, let's just quickly recall the definition of zero knowledge. By the way, in this talk, I'll refer to the definition of zero knowledge many times because you know it's a special case of 2PC. That's a special case of MPC, and also a lot of quantum issues actually already exist or appear when you think about it in the zero knowledge setting. So if you want to solve quantum MPC first, you need to first solve the quantum ZK. Okay, so the definition of zero knowledge is really this simulation-based definition. We compare two worlds, one ideal world and this is a simulated world. In this simulated world, we have a simulator who doesn't know the witness at all. So the definition says that okay, if the simulator can make or can enforce the verifier, malicious verifier, to think that, okay, I'm still in the real world, then that means zero knowledge. Okay. So, but apparently, like, prover knows the witness, but simulator doesn't. So the simulator has to have some advantage over the prover. So one typical way, or one typical advantage a simulator has is the power of rewinding, meaning that the simulator can run this verifier again and again until like it succeeds. Now, the way we think about the rewinding is typically like you have this classical machine, or you don't even think about classical, you just have the machine of V star with this internal randomness, and you run it to a certain point, and then if you're not happy, you just start from scratch. But I would suggest the following way to view it. Like, every time you try, you should think it as like you are making a new copy of the classical adversary. Because if you think it in this way, you'll see immediately that this kind of thing is against the no-clone theorem. Because if the verifier now is a quantum machine, instead of, or in addition to the internal randomness, it could have some internal auxiliary quantum state that is unknown to you. So you cannot freely just make copies of the adversary. Sure, you can copy its code, but you cannot freely copy its quantum auxiliary input. Okay, that's the issue. Okay, for experts, I know that there exists a notion called non-black box simulation, which like potentially doesn't really need the power of rewinding, because for example, simulator, if a simulator knows the code of the verifier, it could do certain things. At least that's true in a classical setting. Okay, I do want to mention that things a little bit different. In the quantum setting, we have very, very limited understanding of non-black box simulation in the quantum setting. And also, the only non-black box simulation technique we know, it also requires a certain flavor of rewinding, which I will show you later. Okay. Now, with this background, I can talk about our agenda today. My talk will consist of two parts. In the first part, I'll talk about the relation or interaction between so-called traditional MPC, the MPC you can imagine, the MPC you are familiar with, how it interacts with quantum computing. I'll show you like what are the technical challenges and what are the progress, and also possibly show you some potential research opportunities so that you or your student can work on. The second part, I will talk something what I call non-traditional MPC. So this notion, like, it just means something you cannot do using classical tools. You know, when quantum comes, it's not only adversary who could benefit from it, honest guys could also benefit from it, right? So with this new quantum power, is there anything we can do so that classical parties cannot do? Something quantum exclusive. Okay. Here, there are actually many examples. So I will mention like two of my ongoing work. The first one is called what I call like spatial temporal MPC. The second one is intrusion detectable MPC. But probably I will only have time to talk about the first one. Yeah, let's see. So let me start from the first part. For traditional MPC, for this part, you mostly see this split of screen. On the one side, I'll like put all the classical known results, and on the other side, I will put the quantum analogs of the things. So I do this because I want to help people who are not that familiar with the quantum MPC, but who's already an expert in classical MPC to see how things go in the quantum. At least you can keep using your classical map to a certain sense, like guide your like journey in the quantum side, so that you see where you are. Okay, so the first thing is a definition. Everyone knows that this notion of MPC was proposed during 1980s by the work of Xiao and GMW. Now here, I want to ask about the quantum analog. It seems there's nothing to ask. It's just definition is the same definition, right? But if you think about it carefully, actually we have two possible definitions. The first definition is something called post-quantum MPC. I'm not sure this is a good name, but if you see this word post-quantum in the literature, it typically means the setting that all the honest parties and the protocol are totally classical, including their computational power and their communication channel. They can't do anything quantum. The only quantum element is the adversary. Okay? The adversary could attack in a quantum manner. So here I'm citing this work VDG. This is actually one person's. His name is Van der Graaf. This work is his PhD thesis. I think this is the first documented work that indicates that rewinding could be an issue in the classical in the quantum setting. Actually, he mentioned this issue in the context of zero knowledge, but once you see this issue in the zero knowledge setting, it's actually general. It has to be in the MPC setting as well. That's why I'm citing this work. Also, we could have another alternative model where, okay, if your honest parties are also quantum, that's different from, it's more fair in a sense compared to the post-quantum setting, because if you allow quantum power to the others, you should also allow quantum power to the honest guys, right? So this is a model. I don't think it has a common name. Here, I'll just call it a fully quantum setting, or some people call it a multi-party quantum computation. If you see MPQC, it typically means it's a fully quantum setting. The first work that clearly proposed this, explicitly proposed this notion is work by Krapel, Gossman, and Smith in 2002. In this model, everything is quantum, including the communication channel. And also, one important thing is once honest parties become quantum, you can start to compute some quantum functionalities. For example, there exist certain functionalities. For example, if you want two parties to interact with each other to prepare, for example, entanglement states. This type of task you cannot do just using a post-quantum protocol, because all the parties classical, they cannot do anything quantum. So, but actually in this talk, I will not distinguish too much between these two models, because in 2020, there's work by James Bartuszek and others. They built a compiler saying that if you know how to do post-quantum MPC with probably 5 extra rounds, you can lift your result to the fully quantum setting to compute the fully quantum MPC. So there are like certain properties if you care. For example, if you care about does it preserve the communication complexity and computational complexity, that's like a further optimization you can ask. But if you just ask for possibility or feasibility, this is already very good. Like at a conceptual level, because of the existence of such a compiler, you don't need to distinguish too much about these two models unless you care about certain advanced properties. Okay. By the way, this compiler is information theoretic in the sense that if you think your post-quantum MPC is a ideal model, like if you have a ideal functionality for post-quantum MPC, then this compiler doesn't add any extra assumptions. Now, since you have the definition, next question to ask is the initial feasibility results. In a classical world, the proposal definition and the constructions, it came at the same time. In Yao's original paper, he built this semi-honest 2PC. One thing interesting is the actual security proof was given probably 30 years later by Lindell and Pincus. Then just 1 year later, JMW found a construction in the malicious security setting, and in the same paper they also lift 2PC to the general MPC. Okay. Now, what is a quantum analog? So the first semi-honest two-party quantum computation was actually given by Dupuy, Nielsen, and Selville. I think Nielsen is at Aarhus here. Then 2 years later, the same set of authors lifted construction to malicious security setting as well. These two works represented early day results, and arguably, I think during this second tenth of the 21st century, you can see that the research in quantum MPC is not that active, because it takes 8 extra years to eventually lift the 2PQC setting to the multi-party setting. Okay, but I think starting from 2020, this research direction attracts more attention, and you will see we see rapid progress in this area. But there's one thing interesting I want to mention, that the first work for post-quantum MPC actually comes after the fully quantum setting. Interestingly, this work, one assumption of this work is that assume that you have a post-quantum MPC, then I can tell you how to do multi-party quantum, fully quantum MPC. But they didn't really build this post-quantum MPC. It's 1 year later, the work by Agravo et al. They built this eventually this post-quantum MPQC. MPC. Okay. Now you have the initial set of feasibility results. What is the next question to ask? To me, the next important question is asymptotically optimized results. That means, can you have a constant round construction with minimal assumptions? Okay. Of course, you could have different opinions. There are other important questions you want to ask, but to me, this is the next interesting question. Here, in the classical setting, minimal assumptions means semi-honest OT. That's the minimal for multi-party computation. So this question was answered by two concurrent work, one by Rachel and Rafael Paz, and the other work is by Vipul Goyal in 2011. Here, of course, the natural question asks, what is the quantum analog of this? But before that, I want to mention one very, very interesting technical point. I don't know if you have realized that or not. When it comes to constant round construction, when we are talking about ZK and MPC, you use expected polynomial time simulation as something like standard. Sometimes you don't even question about it. Why? Because actually there's an impossibility result by Barak Lindell in 2002, saying that if you are having a black box simulator for zero knowledge, and thus for MPC, you have to use expected polynomial simulation. Otherwise, the strict PPT time is impossible. Or you can use some non-black box simulation techniques. In the classical setting, we do have nowadays we do have several candidates approach, starting with starting with the earliest one by Barak. Okay, so why I'm mentioning this? Because this point becomes even more interesting in a quantum setting. Because in a quantum setting, if you restrict yourself to black box simulation, even expected running time is impossible. So here, this notion expected QPT is just expected quantum polynomial time. It's analog of quantum analog of PPT. So this result is pretty surprising. There are two works. First work by Xiao et al. They proved this impossibility in the post-quantum setting, meaning all the parties are classical. But still, whether you can bypass this impossibility if honest parties becomes quantum was open. Just like this year, Jia Chong, me, and Jiahui Liu, we finished this round of research proving that the same impossibility result extends to the fully quantum setting as well, meaning that even honest parties are quantum, still you have to respect this impossibility. Actually, I just gave a talk for this 1 week ago at Eurocrypt. This is very interesting. I want to talk about that, but I don't have time today because I have something more interesting to share later. So if you are interested in this work, you can refer to my Eurocrypt talk. Now, given this impossibility result, so what do we know about the constant round constructions? There are two approaches you can go. First, you resort to non-black box simulation. Okay. If you are using non-black box simulation, constant round construction is possible, and there is a work by me, Pandi, and Yamakawa. We did it assuming LWE. Whether you can do that assuming semi-honest OT, currently there's no paper claiming this, but I believe this is not that hard. Probably if you sit down for a little while, think about it for a little while, you will solve it. So I would just say that this work, maybe if you think harder, you can also make it from semi-honest OT. An alternative way is to target something called epsilon simulation. So this notion, it just means that you give the simulator a parameter, epsilon. This epsilon is a 1 over poly. Okay. It's a 1 over poly function. The simulator's running time will depend on the inverse of this epsilon. And also this epsilon represents the accuracy of the simulation. You can simulate up to epsilon error. Okay. So this notion is interesting because if you have epsilon simulatable zero knowledge, even though it's not as good as the original zero knowledge, in the original zero knowledge, epsilon is just a negligible function. But it at least implies interesting notions like WI, witness indistinguishability. Okay, so in most of the case, you can just use this epsilon simulation in as a replacement for standard DK. Okay, yeah. It's in next slides, but in short, virtual construction is a polynomial round. So here these are. Yeah, not highly non-trivial. Actually, I will talk about that later. But I just want to say that this impossibility is only in the constant round setting. Okay. No. This work is for post-quantum setting. This work is for fully quantum setting. Both of them are impossible, and these two papers are like difficult in different perspective. The first one, the main difficulty is how do you prove something that's possible in the classical setting, because expected PPT is possible in the classical setting. Here, it becomes impossible in the quantum setting. That's the main contribution of CCLY21. Yeah, no CRS. Of course, if you have a CRS, typically you will have a straight line security proof. Those type of proof, typically it's easy to lift it to the quantum setting. But I won't say always. Typically it's easy. Yeah. So this impossibility was initially proven in the setting of zero knowledge. Yeah, I just said them because it's the MPC talk. But when you are talking about impossibility, yeah, they were initially proven for zero knowledge. Yeah. Okay. Here's one more thing I want to mention. I just want to mention, I don't have time to talk, is when you think about constant round constructions for MPC, one very technically challenging point is you need to solve the problem of non-malleability in constant round from minimum assumptions. Or actually from OT, but it doesn't make too much difference if you want to solve it using OT or one function, in my opinion. So I don't have time to talk about why, but if you want to have a constant round MPC, you need to have a constant round non-malleable commitments or non-malleable zero knowledge. So this is also a very rich line of research. Indeed, these two works by Rachel and Pass and also Goyle, they solved the constant round MPC problem by building the first non-malleable commitments in this in constant rounds. Okay, then this work LPY23 also we solved the post-quantum setting by build the first post-quantum non-malleable commitments in constant rounds. But unfortunately, I don't have time to talk about this. I'll skip this for something more interesting. What is something more interesting is I think most of you are here to see what you can do or you can contribute to this long research. That's what I'm talking about. Basically, up to here, basically that's all the history. If you proceed one step further, you enter the forefront of the research in quantum MPC, and basically you can ask, since the symptotically optimal solutions are already known, now the next question you can ask is for more desired properties and for the optimization. Okay, so I have some examples. For example, you can ask, can you do black box constructions, meaning that your construction uses its building blocks by its input-output interface. This typically gives you more efficient construction. I have a paper solving this in the post-quantum setting, but the fully quantum setting remains open. Here, also something interesting I want to mention that in the fully quantum setting, currently there's a theme of research saying that probably standard like post-quantum one function is not the minimum assumption for cryptography. If you are allowed to use quantum communication, pure quantum power, you could have something like pseudo random states or a one-way state generator. They are like a purely quantum. There are evidence that they could exist even if P equals NP. So this is something really quantum. Here, if you are really asking for minimum assumptions, sure, for post-quantum construction, you can still say, okay, OT is the minimal. But for fully quantum setting, it's unclear. Probably like there's something weaker than OT. Actually, that we already know, like post-quantum form post-quantum function will also work by Rachel. You can build multi-party quantum computation if you allow quantum communication. But possibly post-quantum one function is also not the minimum assumption for multi-party quantum computation if you allow honest parties to be quantum. So that's why I'm saying it's a very interesting like open research direction. Also, you could ask for concrete efficiency and exact round complexity. Probably you'll be doubting because okay, I wouldn't worry about this problem until I see like quantum computers becomes available, at least in the near future. But here I want to say that I'm asking this question for the post-quantum setting. Your honest parties or protocol can still be classical. But possible, it's totally possible that adversaries, they are willing to pay more money to acquire the quantum power earlier to attack your protocol. So we'd better switch to post-quantum constructions first. So for this kind of construction, since everything is classical, you could still meaningfully ask concrete efficiency, exact complexity. This is a real-world concerned questions. Okay. Our next question is composable security. Again, in a plain model, as Yuval mentioned, if you have a CRS and if your security proof happen to be straight line, then things becomes a little bit trivial. But if you're asking this question in the plain model, I think it's a very, very interesting question because it touches upon the hardcore of the quantum-driven techniques. This is place I want to take a closer look and show you some technical insights. Okay, let me start. So to think, let's first go back to the most simple setting. This is the Sigma protocol with a single bit challenge. In a classical setting, it's almost trivial to prove that this is a zero knowledge. Again, I'm asking for malicious verifier zero knowledge because if it's an honest verifier, it's trivial. But think about how you do this in a classical setting. You simulate by guess the random challenge B. You can keep guessing until you guess it correctly. You will spend probably expected polynomial in time. But if you think about this question in the quantum setting, now this malicious adversary could have a quantum auxiliary input. This, because of no cloning theorem, the classical rewinding or keep guessing until you succeed technique doesn't work anymore. Because once you consume one copy of the verifier, and if you didn't guess it correctly, you don't have the second chance. Okay. That's a main issue of quantum rewinding. It already shows in this very simple question. Actually, that's where I would mention Watros. So that's Yuval mentioned. Actually, if you ask me what is the most important lemma for the whole area of quantum zero knowledge MPC, I would say it's Watros lemma. It's this lemma. Now I'm going to introduce this lemma to you. This is the assumption for this lemma. It says that assume that you have a quantum algorithm U. It's so nice so that for any given input psi, you run this algorithm with a 0 tensor psi. It gives you this clean structured output. It's a two-branch superposition where the only thing I want you to focus on is the fact that this amplitude or probability P is independent of the input state psi. Okay. Basically, you have algorithm. No matter what psi you give to it, it always splits the state in this clean way with the amplitude independent of psi. If you have such a good quantum algorithm, you could build another quantum algorithm W that only keeps this 0 branch and it drops this 1 branch. Okay. First, let's understand the statement of this most important lemma. And also the size is proportional to the size of U divided by P. So informally, you can memorize this lemma as follows. Probably you have some quantum algorithm. It could generate superposition of 2 branches. So 1 branch is a thing you really care, you want. But it always have some garbage branch that you don't want. Okay. If you have such a U, as long as your amplitude is independent of your input, then you can have a W that kills the bad branch you don't want. It only keeps the good branch. Yeah, under this condition, P is independent of psi. Okay. So once you have this lemma, let me show you how to solve the quantum rewinding issue here. So we will use this lemma in the following way. In our setting, the U will represent a quantum procedure. Basically, you guess the verifier challenge bit B, and then you simulate. I think assume that if your guess is correct, the simulation is almost trivial. If you just for honest verifier ZK, if you know the bit in advance, the simulation is trivial. So here you guess it, but there are 2 possibilities. You're gonna either guess it correctly or you're gonna guess it wrong. Okay. So here in our setting, this is a 0 branch represents the case that your guess is correct, and the 1 branch represents the case that the guess is wrong. Okay. The beauty of this strategy is whether your guess is correct or wrong is independent of the verifier's state size. Because if you just guess randomly with probably exactly half, your guess is correct. Okay. Now you can invoke this lemma to keep the zero branch, which is your guess is correct. That also means correct simulation. Okay. So that's the idea, like one idea why you can use virtuous rebunding to solve this simple setting, 1 bit zero knowledge, or 1 bit challenge zero knowledge. Why I'm mentioning this simple setting? Because this simple setting is actually behind every known construction in quantum MPC and decay. So it's for a little bit different reason, because previously I showed you a 1 bit challenge setting, but you all know that actually to have negligible soundness, your challenge for zero knowledge protocol is typically like a polynomial long. So how does that relate to the example I mentioned? Actually, for a general construction, like if you have a post-quantum or quantum zero knowledge, no matter how long your challenge bit is, we typically follow a common template. Basically, we build 2 simulators. One for a verifier that you assume that it never aborts, and then the other simulator is for verifier that always aborts. So typically, a simulator for always aborting V star is easy. You just output abort. But this simulator for non-aborting verifier is very, very hard. To do this, you typically require extra ideas and new techniques. This is something I won't talk today. Here, the thing I want to mention is that if you conquer all the difficulties and build such a simulator for non-aborting verifier, and also together with the trivial always aborting simulator, you have these 2 simulators, right? Your story is not done yet. You need to wrap up your construction or your simulator with a layer of virtuous rebunding, in the sense that you need to assume that you need to guess whether the verifier will abort or not, so that you can use the corresponding simulator correctly. So I'm not saying that this is the only approach. I'm saying that this is a common template used in the literature. And as far as I know, there's only one exception to this framework. And also, I don't want to mention that one, because if you look into that one, internally, it's just used virtuous in a black box manner. If you open its proof is almost the same as virtuous lemma. If you want to use virtuous lemma in a black box way, that's the only way to use virtuous lemma. You build 2 simulators, and then you guess if the verifier will abort or not. Your guess, again, will be correct with probably exactly half. Okay? Then the virtuous lemma can help you to glue these 2 simulators together to have your eventual simulator. You can safely say that that's the only known technique if you want to build any quantum zero knowledge or MPC. Okay, but that's also the technical obstacle if you consider the concurrent setting. Instead of a fully concurrency, just focusing on this k-parallel session setting. There are like k-parallel sessions of the same protocol running between an honest prover and a malicious verifier. You will quickly realize that the verifier has 2 to the power k ways of aborting, right? That means if you want to guess, if you want to follow previous template, if you want to guess the aborting pattern correctly, your probability is super, super low. And now I want to bring your attention to this something probably you didn't pay attention before. The running time of the W algorithm, which is essentially your simulator, is actually proportional to the inverse of P. So this exponential simulation time issue is the hard core of extending what we know in the standalone setting to the concurrent setting. You can see it's even in the parallel setting, we don't know how to solve it. Okay. There exist some partial results. If you, for example, consider bounded concurrent setting, meaning that you know an upper bound on the number of sessions in advance, then you can do something. I can tell you that roughly the idea is that if you know the number of sessions in advance, you can create more rebunding slots so that you can always, it makes your guess easier to avoid that super exponential curves. But if you look at the unbounded setting, we almost know nothing. There is the impossibility result saying that unbounded concurrency is indeed impossible, assuming the existence of a post-quantum wave function. However, there are several interesting questions. The first one is bounded concurrency. How about can you do that in constant rounds? So these works, they did bounded concurrency. As I said, they need extra slots to simulate. Then it increased the number of rounds. Actually, that number of rounds should be dependent on the priority known bound of sessions. Here, one interesting question is, can you do this in constant round? Actually, this problem is, in my opinion, is as hard as asking for unbounded concurrency, because it touches upon the same technical core of this virtuous reality lemma. Okay. And I just want to say that in a classical setting, this problem is solved by referral paths using OT plus hash function. You do have a constant round bounded concurrent classical MPC. Okay. But in quantum setting, it's open. And in my opinion, it touches upon the technical the difficulty core. Also, this impossibility is for MPC. You can ask this question for zero knowledge. But for zero knowledge, things are worse. Like, we know nothing. No feasibility and no impossibility result either. Classically, we know it's a CKPR lower bound for concurrent ZK. It's a O2.log(n) rounds. But in the quantum setting, like, we don't even know how to quantize this impossibility result. Yeah. So this situation is very interesting to me. Yeah. Anything non-trivial about concurrent zero knowledge, yeah, it will be a big technical progress to me. Okay, that's all I want to say about the traditional MPC in the quantum world. For the remaining 15 minutes, probably, let me mention something refreshing or totally different. Again, I want to emphasize that today I will show you one example of spatial temporal MPC, but this is not the only quantum exclusive notion of MPC. There are more interesting works if you are looking into the literature. I'm showing this just because to me this is interesting and this is my ongoing work. Currently, like, I think I have a fresh memory about it. So, what's this? Let's imagine a situation like you have a company called Closed AI. It serves users in different countries and different locations. For this company, they need to use the geographical information to make their policy. For example, they set different subscription prices in different locations, and they also need to collect user statistics from different locations. Also because some political reasons, there exist certain regions that they cannot serve. But this is typically not a problem because we have things like a VPN. This tension actually represents a very interesting setting. I think there's something missing. The setting is, this is a multi-party computation setting if the users want their privacy. And also if this is closed AI, so of course the AI company also want to keep everything closed and private. But the functionality actually they want to compute is location dependent. Okay. And also user statistics could be some aggregated data. So it could depend on the user's location, but it's definitely not a good solution if you just ask the user to report their location to the closed AI company directly. Or because of the existence of VPN, that's impossible to verify. Okay. So here the setting basically is we want MPC with this location independent function. This scenario is not alone. There are several similar scenarios. For example, we all know the problem of anonymous voting. But imagine an anonymous voting setting where different votes in different locations, they carry different weights. I think this would be a typical assumption, for example, for the election for America. And also, there are some location-based AR multiplayer games or systems. In these systems, users or devices at nearby physical areas typically need to compute some shared object placement and also occurrence maps and so on. So in these settings, we do need certain information about the location, but we don't want to reveal location totally. Okay. So that means we need an MPC notion that could compute location dependent or even more general time, space dependent information. So here, our solution is this spatial temporal MPC. Actually, once you realize this need, or if you analyze these scenarios, come up with such a notion, idea that we need such a notion is not that hard. What is hard is next questions, like how do you define it? And if you can't define it, how do you build it? So that's the question I'm going to talk about next. Before going on, I want to say that this is based on ongoing work with Fuyuki Kitagawa from NTT Social Informatics Laboratories, and also my student Ziqing Guo at COHK. First, definition. So our definition can be split into two steps. First, we treat the location or the position as a literal, like strings. So here I'm referring to the real world, ideal world simulation paradigm, where the ideal world is just as usual, but we append to each party's input a location. Now, so far, the location is just a string. For example, it's a position for a party could be just a string Aarhus. Okay. Also, I'm mentioning everything. I'm talking about everything in the two-party setting. It's natural to extend to multi-party setting as long as you once you understand it. So I'll keep talking in this two-party setting. This is a two-party computation protocol where the first is just append the string or location, string the location at the end of the computation. Now the ideal world is just modify the ideal functionality to compute the function using the literal, using the string. Okay. Now let's see what if Alice is corrupted. Like if Alice is corrupted, as usual, as in the standard 2PC definition, we require the existence of a simulator that actually internally talking with this adversary and extract its input. Now the input takes the form of actual input concatenated with location information and send it to the ideal functionality. This ideal functionality is doing the standard thing. So far, like we are the same as in the standard definition, just that we attach the location information as a string at the end of the input. Of course, the crucial question is why should I trust this location? Sure, your simulator extracts some location, but now so far it doesn't have physical meaning. It's a string. The adversary could make up the location. For example, it's using VPN. This position is Japan when he's actually in Hong Kong. Okay? So the real virtue of our definition is to solve this problem. Why should we trust the extracted location? Our solution or our slogan is I prove, therefore I am. What does that mean? We will trust the extracted location if and only if the simulator could prove it. Here, note that I'm asking the simulator to prove it. I'm not asking the adversary. Okay, so first of all, the question is how can you prove the location? Right? This actually is already known primitive. It's called quantum position verification. That's the part that makes this notion quantum exclusive. You cannot do this in the classical setting. Before I talk about my definition, I'll first review quickly the quantum position verification in case you don't know. So, as the name tells, the position verification is just an interactive protocol where the prover can prove its location. For example, the prover says that, okay, I'm at Aarhus, and he's proving that to a verifier. Eventually, after interaction, the verifier output accept or reject. We want standard things. Companies, if the prover is really at Aarhus, then the verifier accept. And also, soundness as you expect. If the prover is not at Aarhus, then the verifier should reject. Okay. I just want to mention that, emphasize that this notion is impossible in the classical setting. Like, you have a quick proof because there exists a VPN. So this is impossible in the classical setting. But I'll show you how this is possible in the quantum setting. There are already very rich literature in this topic, but I will show you one of the simplest construction. First of all, I'll talk about it in the very simplified setting that the world is literally two-dimensional. It's a line. And Aarhus happens to be the center of the world, at 0.5 position. Now, for this primitive, we need two verifiers. Actually, you can think of them as one verifier, but just putting two devices at this two ends of the line. But you can prove that this notion is impossible if you just have one prover at one location. Okay. The protocol has two phases. The first phase is processing phase. In this phase, first we sample two random strings of length n, where n is the security parameter. Then we encode each bit k using this bit b. This encoding is quantum. Actually, if you know the work of BB84, it's just BB84 encoding. Look at ki, bi. The ki will be encoded depending on the value of bi. Depending on value, if bi equals 0, we do something called computational encoding. Basically, we sample, if ki equals 0, we set it to be cat 0. If it's 1, we set cat 1. But if bi is 1, we do a Hadamard encoding to the classical bit ki. Now, if ki is 0, we prepare a plus state. If k is 1, we prepare a minus state. You don't need to worry about too much about these techniques. The only takeaway is if you know this quantum encoding and the B string simultaneously, then you can recover K. Otherwise, you cannot recover K. You are bound to make mistakes. So for decoding, you need to know both B and this quantum encoding. Okay, that's the only thing you need to know. Okay. Now, in the online phase, we give this classical key to both verifiers, and we give this B string to one of the verifier, and we give the quantum state, quantum encoding to the other verifier. The protocol works by the two verifier send simultaneously message to this prover. The verifier send this string B, this verifier send the quantum state, quantum encoding. At the moment that the prover receives both data, he could successfully decode to learn the case and send the case back. Okay. The verifier will accept if they receive the correct K at the correct time. What do I mean by correct time? Like here, we don't need to consider speed of light. So let's say there's the distance. An honest prover will receive B and then send K immediately. So that means the waiting time for the verifier will be when information, which is light, travels through this 2 rounds distance of 0.5. So if the verifiers if both verifiers receive the correct message K at the correct time, then they will accept. Otherwise, they will reject. So why is this secure? Let's look at a typical attack. If you have an adversary which happens to be at a other position, which is not Aarhus, if you think about the protocol, these two parties are going to send the message out simultaneously. Probably this, or definitely this malicious prover will receive the left information earlier because it's to the left side. But at this moment, he can't do anything because he haven't received the B string. Without B string, he could not decode K. If he decode K, he is forced to make mistakes. So there's nothing he can do. He has to wait until the information of B arrives. Okay? Only after that he could decode and send the message back. However, this behavior is easily detectable because if you count the waiting time of the right-hand side verifier, now it's like the information travels 2 rounds of length 0.7. Then you divide it by the speed of light. That's this time. However, for the honest verifier who's in the center of the world, the traveling time of information is actually 0.5 times 2 divided by C. So this is an inconsistency. That means no adversary can do the same as the honest prover if he's not in the center of the world. Okay. You could argue, okay, maybe this cheating strategy is too weak. What if we have 2 adversaries? We could occupy every point in the line, but just not the 0.5 point. Actually, if you think more about it, let's run the game again. Probably they can receive both adversaries receive the same information at the same time. Again, not a single one of them can do anything. The only thing you can do is to wait. For example, the left adversary could wait for the right adversary to send him the string of B, and then to decode. So basically, one adversary could receive the information earlier, but the other adversary can't do anything. So this actually boils down to the previous case. Like it's most like the case that this adversary just doesn't exist. The information travels directly from the verifier to the left verifier. So this actually reduces to the previous single adversary case. So in this protocol, adding more adversary doesn't really help. I think what you said is the effect you want to achieve, but you really use a quantum mean to achieve it. Yeah.
So because classically, there is a possibility that you cannot really do computation descriptor because instead of having the party in 0, 5, you would have 2 parties on the side that would simulate it.
I wouldn't say that's the only difference, because if you explain it this way, I don't see how you can bring the quantum effects into your proof. Yeah, I think here essentially your proof need to use the no cloning theorem somewhere, right? Probably you can say that we achieved the effect you mentioned just because we use somehow we use non-cloning theorem in a certain way, but I'm not sure if that's the only difference. Yeah, we can take this offline. But anyway, you see that's an example of a position verification protocol. Like it's possible if you are using quantum primitives. Now with this primitive, I can finish my definition. Like now I have this extracted position. So, and I will require that my simulator satisfies two properties simultaneously. The first property is just a standard MPC. It protects the privacy of the input in a malicious setting. But the second requirement is crucial. We require that there exists a secure position verification protocol using which the prover can prove its position. And this position is not arbitrary position. This position must be the position you define, the simulator extracted when you define the first property. So these two properties, they are not isolated. They are closely related by we are requiring these two for the same simulator. And also, this position the simulator proves is really the position you used when you establish the first indistinguishability definition. We require the extraction of such a position. Basically, that's what our slogan says. If you extract something, it doesn't have physical meaning, but if the simulator can also prove this position as the extract position, then really this is where a physical property goes into the computational setting. Okay. Also, note that I'm saying that exist. I'm not asking for all, because like possibly you design this spatial temporal MPC using a certain position verification protocol. It has to be there. But if you build this notion, if you build this construction using a certain verification protocol, typically that protocol is the one you will use to define, or actually when you write down the security proof, you will take that protocol as an instantiation of this secure protocol required by the existential notion. Okay, so as long as the position verification protocol is secure, it must be sound. Then I don't care I don't really care which protocol you are using, as long as you use the sound position verification protocol to prove to me that your extracted position is the position you claimed. Actually, here the adversary will not explicitly claim this position because we also want privacy. Here is the position the simulator claimed by a standard extraction notion of MPC. That's non-virtual for definitional contribution. Okay. Of course, the next question is how can we achieve this definition? Still, this work is ongoing, but I can confidently say that if you give me LWE, standard assumption, I can build it for any quantum functionalities. I put the word spatial temporal means that it's not only a computational functionality, it could be a space-time dependent. By the way, I keep mentioning space-time, but I only show you the things related to location. There's also, you can extend like location-based or position-based to space-time-based computation. That's also known in the literature. It's not something new proposed by us. It's just we use that to define our new notion of MPC. Okay, next, we have another result in the CRC model. LW implies a two-round construction, but this time we didn't manage to build it for quantum functionalities. We only managed to do classical functionalities. First, let me mention why I care about two-round setting. I feel if your construction has only two rounds, the position verification is well defined in the sense that you can safely assume while we are doing the computation, the adversary won't move. Say if you have a protocol that runs for several rounds and there's certain internet latency, I feel it's hard to maybe at the beginning of the protocol, your adversary is at a certain point, but he's keep moving. In that sense, I couldn't imagine how to define position unless you make assumption that during the execution of the protocol, the adversary is fixed in his location. That's why I really care about the low round complexity protocols. But in the CRS model, we only managed to do it for two round. We only managed to do it for classical constructions, functionalities in the two round setting. Then the natural question is, what about quantum functionalities? Can you do that in 2 rounds? The answer is we need stronger assumption, and we are in this. We can only do that in the pre-processing model. Basically, you have 4 rounds in total. 2 rounds will be input independent pre-processing, but the actual online phase is only 2 rounds. It will be interesting to see how do you do that. How do you do the quantum functionality in 2 rounds? But here I also want to mention this is typically very hard, because forget about the spatial temporal. Just for standard MPC for quantum functionalities in 2 rounds from LW, open question. Yeah, you see there's a lot of things you can do just to come to this area. Okay. Yeah, there are some future directions. I guess I don't have time to mention. We can talk about this offline. Let me quickly close the talk by saying that it has been 40 years since the proposal of MPC, and we see very, very exciting progress in the classical MPC world. To me, it will be very interesting to see how quantum computing and MPC evolve with each other for the next 40 years. And of course, this has to be done by a joint force of the whole community. This talk is I just want to spark your interest in this area. You can see there are how many interesting open problems you can work on. Yeah, I hope it gives you some inspiration. Apparently, this is not the last slide. That's because I need to use the last minute to give an advertisement. I'm actively looking for a PC member opportunity for these 2, Eurocrypt and crypto. That's because my department requires me to do so, and I've been a PC member for these many conferences, and also I've been sub-reviewer for crypto for so many years, but I've never been a PC member for these 2 conferences. So I would appreciate that if you are looking for PC members when for this conference. Yeah, thank you. Yeah. That's basically all my talk. I'm happy to answer any questions.
Thank you, Xiao, for the great talk. Maybe the next speaker can come set up, and then in the meantime, we will have maybe time for 1 or 2 questions.
Yeah.
So for this thing of having the position of someone moving in an
Yeah.
could you do something like you say, like the claim position is within the convex hull of where I was during the protocol? Or it's not always to the right of the point?
I think it depends on the application. If your definition, or if you are happy that you prove position within a certain region, you can define it that way. But then you need to worry about what if when Aarhus is moving, he's free. He could move even out of the region you define. Then probably you can put some restrictions saying that even less cannot escape this region within the time of this execution of MPCs. It's much harder than just assume that your constraint has 2 rounds.
Okay, let's thank Xiao again.
Thank you.